Hello everyone, I am Ajitha, did my Masters in Power and Energy Systems from Sastra Deemed University, India. I am really glad to present my work in this IEEE ISGT-Asia 2022. So today I am going to present on congestion management in interconnected microgrids for P2P energy trading. So these are the contents that I am going to cover in this presentation. First comes the literature survey, where these papers were referred for this work, where these papers give the basic idea behind P2P energy trading, the strategies for the trading, and how trading is done in the interconnected system. So from these papers, we get the data of optimal location of ESS and RES and the size of the RES in the microgrid, and also the load demand and the generation profile of solar and wind is obtained from these papers. So next is the objective of this work, that is to identify the transmission lines that are being congested in the stressed condition with RES within the microgrid. Next, to identify the optimal size and the location of ESS within the microgrid. At last, to manage the congestion in the transmission system using RES and ESS within the microgrid. So this is the test system, which is IEEE 30 bus system. Here generators are placed at bus number 1, 2, 5, 8, 11 and 13, where the microgrids are being integrated at buses 7, 12 and 21. And the voltage range of these buses are 132 kV or 33 kV. So next is the IEEE 33 bus system, which is considered to be the microgrid, which are being integrated in the transmission line at bus number 7, 12 and 21. So here the voltage range is given as 12.66 kV. So the DGs are placed at the optimal positions, which are referred from the reference paper. So at bus number 13 and 30, solar generation is kept of corresponding capacity. And at bus number 6, the wind generation is kept of corresponding capacity. So the total load demand is also given. Next is the graph which is showing the load demand, power from the PV and wind for 24 hours of the microgrid where the DGs are present. So next is the properties and sizing of ESS. As we know that this work is related to the congestion management using ESS. So the sizing of ESS need to be done. For that, SOC need to be calculated. SOC means state of charge. So state of charge while during charging and discharging need to be calculated. So these are the notations used in this formula, where state of charge during the time period is given, where the power exchange during particular time period is given, the charging efficiency, discharging efficiency, as well as the nominal capacity is given. So from the reference paper, the charging and discharging efficiency is considered to be 88%. Minimum SOC limit is 20%. Maximum SOC limit is 80%. So for this case, 3 cases were referred and compared, where the charging is done after 12th hour, that is from 13th to 16th hour, where load demand is considered to be very less than the generation. So the excess energy can be stored in ESS. For that, at 12th hour, it is assumed to be at 20%. So SOC is calculated for every hour, and it is obtained that 1.5 megawatt is utilizing the maximum capacity of SOC, that is 71.68 percentage. Hence 1.5 megawatt is the suitable one in this case. So next is placement of ESS. So for that, 2 cases are compared at bus number 19 or bus number 6. It is also from the reference paper. So we can see when the ESS is placed at bus number 19, which is in the microgrid, the excess energy from the microgrid is stored in the bus number 19th ESS. So when the ESS is placed at bus number 6, it is being integrated with the DGs present in that place, which is the wind energy. Wind energy is considered to be integrated with the ESS present at bus number 6. So excess wind energy can be stored in the ESS and it can be used for reduction in the congestion management. So next is the load flow analysis. First, forward and backward sweep method is used for the radial system. where different cases is present, and the slack bus power is fed to the transmission system, where NR method is used to find the power flow in each transmission line of the transmission system, and under stressed condition or without any stress. So there are four cases where case one is the placement of the microgrids one by one at bus number 7, 12, and 21 of transmission system. Next is case number 2, whereas DGs are present and it is without DGs. And case number 3, where stressed condition is created in the transmission system. So under stressed condition and without stressed condition. Stressed condition is created by outage of a line, that is line number 15 in this case, because at the bus number in the IEEE 30 bus system, the line number 15 is considered to be the most critical line of the system. It is from the reference paper. So it is outage, it is considered to be the stressed condition creating in the transmission system. And also the case number 4 is by placing the ESS at the optimal location, that is bus number 9 or bus number 6. Next is the analysis of these cases. So by comparing all these cases, we get to know that by placing microgrids without DGs tend to increase the load flow of the system, where the lines power flow get to increase, and by placing DGs in the microgrids, the line flow tend to get reduced. And after creating the stressed condition, we can see that almost same lines are being congested. Hence, when we place the ESS at the optimal location, there is the reduction in the congestion. So this is the results showing the congested lines at different hours when the microgrids and the DGs are present. So we can see that almost all lines, the same lines are being congested in all the hours. So now we are having the congested lines. We know the optimal size of the ESS that need to be placed is 1.5 megawatt. And also we have the optimal place for the ESS, which is bus number 19 or bus number 6. So to select the bus number 19 or 6, we need to find the load flow analysis. So for that, by this table is created. For that, the amount of reduction in congestion with ESS need to be calculated. So by comparing the data before and after installing the ESS in the microgrid, we can compare this and we can find the reduction in the congestion with ESS. So the amount of reduction is calculated by subtracting the amount of power flow in each lines before and after installing the ESS. And bus number 19 and bus, we can see there is more reduction when we place the ESS at bus number 6. So if the congestion has increased in some hours during charging of ESS, it is shown like in from 13th to 16th, it is given in the negative value. And if 0 is given as 15th and 24th hour, we can see there is no improvement in the congestion. If nothing is given in the column, it means the congestion is being totally eliminated during that hour. So conclusion of this work is that we have studied the effect of RES, which is placed in the microgrid, how it is affecting the transmission lines, and we have seen how the amount of congestion being reduced after placing ESS. And for this case, the optimal placement of ESS is bus number 6. So future work is like by comparing the load, ESS and RES profile of each microgrid. We have to perform P2P energy trading, and also the optimal sizing and scheduling of charging and discharging of ESS need to be done to eliminate the congestion. So in this work, we have reduced the congestion. Next step will be to eliminate the congestion. So these were the reference papers. Thank you for the great opportunity.